مرحبا اسمي الطالب عاصم مهيار and today we're going to talk about a transmitter and a full AM modulator. Before getting into all the details, I want to begin by explaining what is a transmitter and how it actually works. So in simple words, a transmitter is just an electronic device used to produce radio waves in order to transmit or send data with the aid of an antenna that we can see right here. But a simple explanation of a transmitter is that it's a device that performs a modulation scheme on our desired signal, which we are trying to send, by firstly frequency shifting that signal, then amplifying it to finally send it to that antenna. And as we know, any signal that we are trying to send needs to uphold modulation first, which as we know, modulation is only frequency shifting our signal to a higher frequency. The reason why we use modulation is to decrease the length of this antenna. Before getting into anything else, I want to stress that our focus in this video is going to be about this block right here of the transmitter, which is the power amplifier / modulator block right here. And before getting into that, I want to explain design specifications that every transmitter has to go through if you want to build an appropriate transmitter. So starting off with your transmitter design specifications, those specifications are very crucial and very important for to designing any transmitter out there. Firstly, I'm going to start by frequency accuracy and stability. Basically, the frequency accuracy of a transmitter depends on the crystal oscillator used in the frequency synthesizer. Every crystal oscillator comes with an error margin, which in hand dictates the accuracy of a transmitter. So, as we've seen right here, we can see that here we have a frequency synthesizer. Obviously, I don't want to get into details of the building blocks of this frequency synthesizer, but it has a crystal oscillator in it. So this crystal oscillator comes with an error margin that eventually dictates the frequency accuracy of this transmitter. Secondly, I want to talk about frequency agility. So frequency agility is the ability of a transmitter to change the frequency. Usually transmitters hop over other frequencies within a certain range. So if you're like on a 90 megahertz range, it would drop down more or less below 90 megahertz or above 90 megahertz, just for security purposes. This is also affected by the frequency synthesizer, as it should stabilize within a desired time. Thirdly, I want to talk about spectral purity, which is a measure of the nonlinearity found in the transmitter. Obviously, the nonlinearity in any transmitter comes from the power amplifier found in that transmitter, which the problem with the power amplifier is that it causes harmonic distortions throughout its output. So that causes nonlinear distortion. So your transmitter needs to have a high spectral purity for better output. Fourth and last, I want to talk about efficiency. As we know, efficiency is a very important specification which affects portable and non-portable transmitter devices. It affects portable devices because it is directly related to the device's battery life. So the higher your efficiency, the longer the battery lasts in your portable device, which can be a mobile. For a non-portable device, having low efficiency causes having low efficiency causes more power dissipations in that device, which requires a bigger heatsink or like a cooling system. to prevent burning of the equipments found in the non-portable device. So rather than spending money on a cooling system or a heat sink just to prevent your your equipments from overheating and burning, we can just improve the efficiency, and by improving the efficiency, we can reduce the power dissipation from that power amplifier or the transmitter as a whole. So as previously mentioned, our main focus was the power amplifier block and how this power amplifier is going to work as a modulator. So as we can see here, this is a Class C power amplifier as roughly as it's drawn. This Class C power amplifier is used for many purposes. One of the purposes is that this Class C power amplifier has a really high efficiency due to the transistor being on only for a short period of time. So in this block right here, we want to see how this power amplifier can work as an AM modulator. But before getting into that, we need to know how, or what is the voltage that comes out of the AM modulator in general. So the voltage that comes out of a AM modulator is V of t, which equals to E of c, which is the amplitude of the carrier wave, 1 plus m times cosine omega m of t. M here obviously is defined as the modulation index, cosine, again multiplied by cosine omega c of t. And the highest number for m can be 1, and the least can be 0. 0 means that there is no information signal in this AM modulation. So ultimately, we want our Class C power amplifier to output this kind of voltage. So before we get how this Class C power amplifier can output this kind of voltage, we need to know what is the output voltage that comes out of this Class C power amplifier. So let's say we have an input of an input signal with this omega n. So the voltage swing for a Class C power amplifier is actually the highest peak is 2 VCC and the least is 0, which gives us ultimately an output signal of VCC multiplied by cosine omega input, and let's just call this omega c of t. Omega c of t. So what we can notice here is that the amplitude right here that is multiplied by this cosine signal is nothing but this voltage right here, which is VCC. So let us just visualize that if we can make this node right here, which is equal to VCC, equals somehow this whole expression, we can ultimately create an a power amplifier that works as an AM modulator. So to summarize this trick right here, as we can see, if only we can change this voltage VCC to equal this expression right here, and let's just simplify this expression to better visualize what we want right here. So this can be translated into EC plus, obviously this modulation index is described by EM over EFC. So when we multiply this, we get EM multiplied by cosine omega m of t. So ultimately, if I can make this voltage right here equal this expression, I have successfully created an AM modulator. And this is basically the trick in this power amplifier slash modulator block found in our transmitter. So as previously mentioned before, we want to see how this power amplifier can work as a modulator, and we said we need a Class C power amplifier. But what we need to find out here is that so let's just familiarize ourselves with the components we have here. Here we have a power amplifier here, power amp, and obviously our studied signal here is an audio signal, and here we have our audio input. Here we have an audio bypass capacitor, just call it audio bypass. So the reason why this capacitor is here is because given that the audio signal is an alternating signal, the capacitor is put here to stop the audio signal from interrupting and allow the signal at this node to be purely DC value. So it's just a bypass capacitor. Here we have an RF bypass capacitor as well. So what we need here, obviously this radio frequency signal is coming from the input signal right here. So the same way the audio bypass capacitor works is that we want this signal to be purely DC, and we want to get rid of this alternating signal. So here we have a transformer. Here we have an audio transformer, and here we have a transformer at the input. So now, since we all got familiarized with the circuit and its components, we're going to start by assuming that the signal that is coming after this audio power amplifier is equal to EM cosine omega m of t. As previously mentioned, our main purpose here is to create the formula for the voltage for an AM modulation using this power amplifier. So here we have our signal coming out of this audio power amplifier, assuming that it's EM cosine omega m of t. Given that it's a Class C power amplifier, and the output of this Class C power amplifier is going to be equal to this voltage right here added to this signal multiplied by cosine omega c of t. So our voltage right here is going to be equal to the voltage here, VCC, plus EM cosine omega m of t, all multiplied by cosine omega c of t. Because as we studied before, this is basically how the output of the Class C power amplifier is. Given that here we have a signal with an with a frequency f of c. So by taking that into consideration, we can also assume that the maximum amplitude for our signal here that's coming out of the audio amplifier is, so E max right here, EM max is equal VCC, only given when the modulation index equal to 1. So M is the modulation index. So when this modulation index equal to 1, we can assume that the amplitude of the signal equals the amplitude of the carrier. So we have EMM equal EFC. And this is how we come up with this output of voltage right here coming out of this power C power amplifier. So we would like to design this power amplifier. So to actually design this modulator, we need a couple of parameters that we need to find based on the power of the carrier. So our main focus here is my power of the carrier signal. So if we have the power of the carrier, we can find out 3 important things that will help us to design this modulator. First thing we can find is the power coming out of the audio amplifier. So we need to find the power coming out of this audio amplifier. So first we have power coming out of audio. Secondly, we can find out Z output, which is the impedance that can be seen from the power amplifier and the impedance of the transformer. The only reason why we want to find the Z impedance right here is to perform power matching between the audio amplifier, which is right here, and the impedance of this audio transformer. So secondly, we want Z output of the audio amplifier. Finally, we would want to find the impedance, which is the Z output for the output carrier. So we would like to find the impedance right here. So let's call that Z output 2. So firstly, we want to find the power at the audio power amplifier. So to do that, we need to take into consideration, or what we need to remember is that the total power, we need to know that the total power equals the power of the carrier, okay, multiplied by 1 plus m squared over 2, m being the modulation index. So to find the power added by the audio amplifier given the power of the carrier, we need to assume maximum total power that only occurs when the modulation index equals to 1. This gives us a power total maximum, excuse my handwriting, being the power of the carrier 1 plus 1/2, given that m equals to 1. What we need to take into consideration too is that the efficiency of a Class C power amplifier is equals the power of the carrier divided by the power of the supply, or the source, which we have right here. And assuming that the Class C amplifier has a very high efficiency, let's just say 100% efficiency, we can know that the power of the carrier here equals the power of the supply. So taking all that into consideration, we can come to the conclusion that the power coming out of this audio power amplifier, PA, obviously at maximum, because we took that power of T at maximum, equals 0.5 multiplied by the power of the carrier, or 0.5 multiplied by the power of the source. So now we've found an expression for the power at the output of the amplifier. What we need to find next is the impedance at that power amplifier, right here, the audio power amplifier, which we denoted by Z output. So we need to take into consideration at first all the information that we have. So we know here from that transformer that the power at the primary coil, right here, power at the primary coil equals that voltage RMS squared divided by Z output. Obviously taking a 1-to-1 ratio for that transformer. So we can find here that the Z output here equals VRMS squared over that power of the transformer. But the power of that transformer is only just the power of the audio amplifier right here. So we can detonate this by that power of the amplifier. Also, here we are only taking into consideration the maximum impedance for Z output. So again, here we are seeking the maximum impedance. For this to happen, the impedance needs to equal the conjugate of the output impedance of that audio amplifier. So Z output maximum, for it to be totally matched, it needs to equal the conjugate of the output impedance of this amplifier. So again, assuming a 1-to-1 ratio, the voltage of the transformer equals, as we know, it equals to the voltage coming out of here equals to EC E carrier plus the E modulated signal cosine omega m of t. And from what we previously been taught is that here the amplitude of the carrier equals VCC, and as previously mentioned is that given that it's we assuming maximum modulation index, EM maximum also equals VCC. So as we found here that, so what we get right here is that the maximum peak voltage that we can find at the output of this transformer is only VCC. So given that, we can calculate the output impedance for this this audio amplifier, which will equal to VCC. Obviously, RMS value, you need to square root all squared divided by the power of that amplifier. But we found right here is that the power on the amplifier is only 0.5 multiplied by the power of the supply. So here we have 0.5 multiplied by the power of the supply. But the power of the supply right here is only VCC multiplied by the current that comes out of that supply. So to make it all into a simpler form, by taking this the square root, we get VCC squared, and then 2 square root squared, you get 2. This comes out at the denominator. 0.5 times 2 gives you 1, and as we know that the power of the supply equals VCC multiplied by IC, here we have VCC squared, VCC, 1 VCC cancels with 1 VCC, so it gives us an output impedance of VCC over ICC. So here we found out the power of the audio amplifier. We found an actual impedance, a maximum impedance for that power amplifier, and now finally we need to find the output impedance for the output right here. So to find the last parameter for this design, we need to calculate the impedance found at the output. First, we need to consider that the output power is detonated by, the power of the output, which is right here, equals the power of the carrier multiplied by 1 plus m squared over 2. But because we want the total power to be transferred to the final stage, which is the antenna, as we've seen in this previous block diagram, so just because we wanted to go to the final stage of the antenna, we will assume that m equal to 0, because we want the power of the carrier to be transferred fully to the antenna. So here we have m equal to 0. So this cancels out this term right here, which leaves us with the power of the output equals the power of the carrier. So to find the power of the output is calculated by V output RMS, which is here, squared divided by Z output 2, which we are trying to find. So I'm gonna move to another slide. So continuing on an empty slide, here we found out that the power of the output equals the voltage at the output RMS squared divided by our desired Z output, or the impedance at the output that we're trying to find. Rearranging this just gives us that the voltage at the output RMS squared divided by P output right here. Since we assumed that the modulation index equals to 0, that just leaves us with, obviously here this is the voltage at the output. So if m equals to 0, E of m, the amplitude of the signal, actually again equals to 0. So this term is gone. So we're only left with VCC. So rearranging this, Z output equals VCC divided by root 2. Obviously this is, because it's an RMS value, all divided by the power of the output. And finally here we find out that the Z output equals to VCC squared. Okay, we can modify this power of the output into a given quantity that we know, which is, as previously mentioned right here, it's only the power of the carrier. So you have 2 multiplied by power of the carrier. So to put everything into perspective, if we have the power of the carrier right here, or right here, we can actually find all our design parameters of the power of the audio amplifier, the output impedance of that audio power amplifier, and finally the output impedance for the modulator. Anyhow, this ends the lecture of transmitters and power amplifier of a class C. Thank you for watching.